Welcome to EDU World Space.
The idea of escape speed is often used in figuring out how much energy it would take in order to get off of, say, a planetary surface. So the idea is launching something off the surface and getting it to escape. So the idea is you can use conservation of energy to figure this out. You would set your initial kinetic energy plus your initial gravitational potential energy equal to zero, with the idea that you end up far away from everything, especially the body you're trying to escape. And you have no kinetic energy. So you're in the middle of nowhere with nowhere to go, I guess. So 1/2 times the mass of the object times the escape speed minus g big M of the body, little m of the spacecraft over r equals to 0. And solving that for the escape speed, and that should be squared, sorry. Kinetic energy has 1/2 mv squared. And solving then for the escape speed, what's true is the small mass of the spacecraft cancels, and your escape speed is independent of that mass. Now, if you're trying to escape a body, what you put in is the radius of the body. So let's take a look at a couple examples. The first case is escaping from Jupiter. And we're going to assume that Jupiter has a solid surface at its upper atmosphere, but we don't even have to do that. We just need to know the radius of Jupiter and the mass of Jupiter. So its radius is given as, let's see, 5 point, no, that's not right. 6.9 times 7 times 10 to the 7th meters. That sounds right. And its mass has to be looked up, but 1.899 times 10 to the 27th in kilograms. And G is a well-known constant. Let's see, 6.673 times 10 to the minus 11th newtons meter squared over kilogram squared. Okay, so fairly straightforward then to calculate that, putting in the numbers in SI units to as many sig figs as we can muster. And provided we used SI units, that should come out in meters per second. And we get of the order of 60,600 meters per second. So that would take quite a bit to escape off of the surface of Jupiter. Okay, so the next thing to realize is you don't really need to be escaping the surface of an object. You could be trying to escape the gravity of the sun from somewhere in the solar system. But the idea would work the same way, is that you have a certain gravitational potential energy initial. And that's supposed to be a little spacecraft, not a fish. And you need a certain kinetic energy to get infinitely far away from the sun. So let's figure out how much it would take to escape the sun if your spacecraft was at a distance, our initial, of 1 astronomical unit. And yes, again, we can go look that number up to whatever number of sig figs we care to put in. We know that number quite well, quite accurately. And so we need the mass of the sun. Which again is a fairly well-known number. And notice that we want both numbers in SI units of kilograms and meters. But the formula works just the same, whether you're trying to escape the surface of a body or get out of the grip of a star. And kind of one of the things that's a little bit sobering is how massive the Jupiter is, about 1/1000th the mass of the sun, which is a little bit sobering to realize Jupiter is that large. Many people call Jupiter a failed sun. And we see that the escape speed is of the order of 42,100 meters per second. So maybe the moral of this story is if you are starting a spacecraft somewhere out near the orbit of Earth, you'd have an easier time escaping the sun than you would trying to get away from Jupiter from its upper atmosphere.